Hi everyone, my name is Kevin. I'm a Security Solutions Architect from Amazon Web Services. I'm delighted to see all of you here interested in security and joining me today to talk about something that isn't commonly discussed, which is security chaos engineering. So, what we'll be talking about today, right? We're going to be talking about what is it for those who don't know, how do we get to security chaos engineering, and then we're going to walk through a sample application. We're going to apply chaos engineering and you'll see it in action. And then we're going to close off with things you can do for your own environment. So this is recorded, which would be fun. But more importantly, I love to keep my sessions interactive. So if you have any questions, feel free to put your hand up, raise it, shout it out. I'll be happy to answer any questions. And if I don't know, I will get back to you after the session. So, first big one, what is chaos engineering, right? So this is literally the textbook definition from the people who wrote the book on it. Funny, so this is Casey Rosenthal, right? Very funny story. I was at Reinforce 2022. This is AWS's annual security conference in the US. We were having a security chaos engineering booth, and Casey Rosenthal actually showed up to look very confused at what we were doing. And we only figured out he was Casey Rosenthal after we scanned his badge and saw his name. So that was quite a scary situation to be in. But at a high level, chaos engineering is the discipline of experimenting on a distributed system to build confidence in its capability to withstand turbulent conditions in production. So let's unpack this a bit, right? So why do we need to use chaos engineering? The first big one is that modern applications have multiple components. You have your web tier, your API, application, data persistence layers. On top of that, modern applications are written by squishy humans, and squishy humans either A, write code which behave in ways that we don't expect them to be, or B, write code, leave it there, never comment on it, and then 10 years later you have been asked to go and modernize it. So code is either poorly written or not commented, people don't know what happens with it, right? So to respond to potential security events, you need to understand the failure scenarios across each component and all their downstream impacts. So this additional complexity, you have applications with multiple microservices written in different languages without right comments on deprecated systems, means that it's quite difficult to predict failure, right? And if you can't predict failure, you can't figure out your unknown unknowns, how can you secure your application? So just as a question, how long does your system take to detect and recover from these events? So throughout my talk, I'm from AWS, so a lot of the examples will be very cloud focused, but principles can be applied to any application. So let's say, for example, you have an API key, right? Straightforward. You have an API key or database access string. How long will it take your systems to detect if that access key, that secret, has been pushed to the internet? Do you have a procedure to respond to it? Will your procedure impact your running production systems? So all of these are things that chaos engineering will try to run experiments, collect evidence, and try and understand better. So let's start off with a sample application, right? So this is a very simple application. It's a personalization microservice, okay? You have some EC2 instances, virtual machines running the application. It communicates to a database. There's an API gateway in the front with a web application firewall. And then there's an upstream service and a downstream service, all straightforward so far. We have a security service called Amazon GuardDuty, right? So Amazon GuardDuty is our intelligent threat detection service. And then let's say one day, GuardDuty detects unexpected activity on the EC2 instance. Maybe it's communicating with a known command and control server. Maybe it started mining crypto. So GuardDuty creates. So I guess the first big question right now for you guys is, if this was your system, would you have any tools to detect if anomalous activity was happening? If your virtual machine started talking to known command and control servers? And B, let's say your system does indeed detect. How long does it take for your system to detect it? How long does it take for your security team to respond to the notification? And what does your security team know what to do in this kind of event? So all of these are questions that a lot of customers, they don't actually know until they put their systems to the test. So let's say in this case, our guard duty has detected something, the automation kicks in, we terminate that instance or we isolate that instance for forensics to investigate, right? But when this happens, we have a whole different set of questions now, right? So, on the surface, this response seems quite adequate. But a few other questions. What other logs do we need for further investigation? Do we know if the credentials need to be rotated? Should other parts of the system be replaced or restarted? And from an operational standpoint even, right? Let's say you take down this instance, and before this another instance is spun back up to respond to it. For all you know, the latency here for your personalization microservice could spike because there's only one instance handling all the traffic, and then your application goes down. So these are the kinds of situations we want to uncover and avoid through chaos engineering. Now, chaos engineering, like what I said earlier, is a formalized process, right? A lot of people think of it as breaking things in production, chaos monkey, chaos gorilla, things like that. But it's not just as brutal as that. So chaos engineering is a formalized process. It's like a scientific process where you run experiments on systems in order to generate evidence. So you're running experiments on complex systems in order to see how they respond, and when they respond, you're generating evidence, and from that evidence you can respond and change the system to make it more resilient or secure. Okay, so why the big difference between chaos engineering or chaos experiments versus just simply testing, right? Is that chaos engineering, when you're testing, you kind of know what the outcome is supposed to be. Like let's say you run a unit test on a piece of code. You know that the unit test is supposed to pass with this output. Whereas when you run a chaos engineering experiment, you are changing as part of a system in order to collect new information, collect evidence of things that you may not have thought of. Those are the unknown unknowns. So the strength of chaos engineering here is to reveal these blind spots which you may not have thought of earlier. Okay, so and chaos engineering, like I said, is to uncover blind spots. And from a security perspective, the key blind spots that we can consider are monitoring, observability, and alarms. I've spoken to a lot of CISOs and a lot of customers. Their first big question is, do I have enough visibility over my AWS environment? So now we know what chaos engineering is, right? Now, how do we merge this with security? From an AWS perspective, we believe that incident response comprises of three main pillars: the people, whether they are equipped; the process, whether they know what to do; and the technology, whether they have the technology needed to actually do what they need to do. So when we put this together, we come up with security chaos engineering, and how it's going to work is that we're going to create hypotheses, we're going to run regular experiments. These experiments help you simulate incident response processes. It's more than just a drill. You are running things in complex systems to see how the system reacts, collecting evidence and applying that, which we'll go into in a moment. And then you take all the data that you generate to improve your people through improved skills, processes through improved runbooks, and technology through more effective tooling. So chaos engineering has 5 phases. Before I dive into it, I just want to pause. Any questions? All good. Alright, cool. Okay, chaos engineering has 5 phases. We're going to walk through each of them. And then hopefully at the end of it, you'll begin to think of how you can start applying some of these principles into your organization, into the way you build applications. We have steady state, hypothesis, and we run the experiment, we verify, and then we improve. Okay? So, how do you start with chaos engineering? Like what I said, it's a scientific process, right? So you start with a document. Okay? I don't have time to go into detail of what this final document looks like. There's a blog post and a workshop I have linked at the end. But it all has to be written down, because just like an experiment, you want to write down your hypotheses, you want to write down the things that you observe, write down the evidence, and writing it all down ensures that you'll be able to share this information and learn from it. So, you start with a document, then the first question we're going to do... Okay, so the first step is steady state, alright? And this is where a lot of customers already start to struggle. When you're thinking of steady state, you're thinking of the behavior and configuration of the system under normal configurations. What this means is that these are the key metrics that you have to look at to understand whether your system is secure and available. Now, a lot of times, customers, when they get started on this, they may focus on metrics which are too technical and not really linked to the business. So like a good example could be something like, okay, so how many vulnerabilities are there in an application, for example? It's a good metric, but it's not linked to a business priority. So it's a better metric, a better understanding of steady state will link it to business priorities, and this helps you understand your system as a whole. So if you don't know what metrics you can think of, what metrics that you may want to look at, you can consider threat modeling. So threat modeling, if you don't know, is just when you take your system, you try and figure out where, what the most likely angles of attack are, you try and figure out where the application will be most susceptible, and then you focus on that. So if you haven't done threat modeling on applications, you really should. Some examples of metrics include, from a security perspective, mean time to detect, mean time to notify, mean time to remediate. That's all very normal things. But more interestingly, from an application side, we have the number of requests and request latency, right? So these are metrics that security teams don't often consider, but are things you got to think about, because like what in our example earlier, your security team takes down an instance and your latency spikes up, and that is not a good outcome for the business. So earlier example, we have latency. Let's say our example just now, request latency should be less than half a second per request. And what could this depend on? So these could depend on, if we do a bit of threat modeling here, your EC2 instances are not overloaded. They are all running at 60% CPU utilization. Your API gateway has WAF, a web application firewall attached with block bots. So this will stop any kind of layer 7 DDoS attacks. And maybe your upstream services request data at a certain rate per second. So these are all assumptions, these are all steady states that you need to know, and you need to write down in that document we talked about earlier. If you don't know this, then it's a sign to start investing in better tooling, in better processes, and in better documentation to write all of this down. Alright, cool. And then, okay, so yeah, document. So we add to our document, all these are our cool metrics, right? So now with our steady state, now we understand what our application looks like under normal behavior, we start with a hypothesis. So security hypotheses usually take the following form. When something happens, some system will notify the team within a certain amount of time. It can be challenging to think of a hypothesis because you don't know what to break in your system, right? So our recommendation is you start with something there's a real world event that is likely to occur that can impact user experience. So a great example of this is like our previous example, your instance has malware detected. Is what do you do then? Your instance was your application was deployed to production, and then you discovered a vulnerability in your application. Can your systems roll back? Can they stop the deployment? How do you answer questions like that? So some examples here. Let's say these two are examples that we see quite often with customers. If port 22 permits unrestricted access on a security group, we have a service called AWS config. It will detect it. It will run some automation to remove that rule. It will notify the team through Slack within 5 minutes, and the application latency is no longer affected. So you see all the elements are there. We have the system, we have the security misconfiguration, we have the business impact that the latency will remain there regardless of what happens, and we have what the security team should be doing. Second example, if malware is run on an EC2 instance, Amazon Guard Duty will detect it within 15 minutes, notify the security team, it will run the playbooks. The playbook should not affect the application's error rate, for example. So these are examples of hypotheses that you can think of from your business. So like what I said, keep it focused on business outcomes and metrics, right? And remember, hypotheses don't need to be complex when you're starting out. Even simple experiments can yield a lot of good data. So a great example of this, and this is a workshop we ran at Reinforce, right, is where the experiment was essentially that if an S3 bucket was exposed to the world, our system will detect it within a certain period of time. And the number of requests to the bucket should not spike, for example. And what a lot of customers found out while doing the workshop is that guard duty actually has a 10 to 15 minute delay before it generates the finding. Config actually has a 5-minute delay. So this is how chaos experiments uncover all of these things that you may not have thought of or you may not have known about. Now, the next part is the most fun. It's where you where you come up with the experiment. You have the hypothesis, then now you come up with an experiment to test that hypothesis. Now, this is where a lot of customers get very scared. They think, okay, what if I run the experiment and it breaks and my boss kills me, things like that. So the important thing to remember is that you can start in staging, right? You don't have to start running experiments in production right away. It's actually really helpful to begin running in staging, building that confidence to run chaos experiments, and also demonstrating the value of your work to your bosses. And that helps you earn trust with the rest of your organization. And one thing really cool about the cloud, right, is that because the resources are scalable and ephemeral, you can actually set up a staging environment to be identically configured as production, and this will allow you to get a lot of great evidence when you run experiments, even in staging. So yeah, the closer you get to your production environment, the better. And on top of that, when you run an experiment, it's not like, okay, let's just delete this EC2 instance and see what happens, right? It's a very formal process. So when you run an experiment, you have essentially a kill switch there. So you are looking at a certain metric, and then if that metric goes above a certain amount, you know your hypothesis has been disproven, and you want to kill the experiment before it goes too far. So that's a really important part of chaos engineering as well. It's important to know when you need to stop the experiment and when you need to roll back. Okay, and what else is there? Yeah, okay, so from an AWS perspective, we have a service called Fault Injection Simulator. It runs experiments for you natively. You can orchestrate pretty complex experiments with it. I'm not going to go into too much detail, but what's important for security practitioners like you is that even though security actions are not supported out of the box, you can run systems managers documents to simulate security events like a port being open to the world, an S3 bucket being exposed to the public, malware installed on an instance. You can do this through systems manager documents, orchestrate it through fault injection simulator, and you can get started there. Okay, but pause here. Any questions before we dive in? Alright, great. Okay.
One question.
Oh, yes.
How do you manage when there is a new version that is put into production? The problem is versioning. Because if you put some metrics, you say, okay, I need 0.005 to be reached, and then after there is a new version, how can you update the system every time? I think this looks good maybe for static system when there are not too many versions. Or is there a way to update the metrics that you mentioned easily?
So that's a great question. And so from what I understand, you're asking if, let's say, for example, you have a very complex system where the metrics are changing and you don't know at
every time you have a new version, yeah.
Correct. And that's a great question, right? So that is more of so when you begin to run experiments with systems like that, how do I put this? In the observability world, there's always the concept of the 99th percentile, right? So if you don't want to use a fixed metric, you can use the 99th percentile point. So let's say latency, for example, it changes based on day to day, but you can set the limit as the 99th percentile latency can never go beyond that point, and that's a mathematical tool you can use, for example. Does that answer the question?
Yes, it answers partly. The other issue we have is when you simulate traffic.
Yes.
If you simulate traffic and you don't know if it's normal to have a big quantity of traffic that impacts the application. Sometimes it's normal. For example, you are selling something, many people connect at the same time to your application, and there is an impact. Is it because of security issue? It's like a DDoS starting point, or is it just normal behavior because there is a special business situation that happens?
Okay, good question as well. So that is another observability question, right? That's why we said at the start about the steady state. So you first need to know, let's say, for example, you have a school management system application, you have students logging in at 9 a.m. every day. You know that 9 a.m. every day you're going to get a spike. You know that is your expected behavior. But if you get a spike at 3 a.m., then that may not be expected behavior, and then it's a fair chaos experiment to run. Let's say, for example, we get a spike in traffic at a point where we don't expect it. How does our system react? So that's a good question. Any other questions? Great. Okay, so you've run the experiments. Let's say you've run the experiment I just described, right? You have a system. Let's say it's a school management system. Every morning, 8:30 a.m. before everyone logs in, you scale it up so that all the students can log in. And then after school ends, 5 p.m., you scale it back down, and then you just keep it running on a low capacity till the next day, right? But what if you get a huge burst of traffic in the middle of the night? So you want to simulate that. So you go into your staging system, you start at maybe like 12 a.m. unfortunately. Sometime when your system's not expecting it, you send it a huge burst of traffic, and then you see what happens, right? So you see what happens, maybe your system can scale up. So a few questions you can answer. Does your system scale up? Is there a notification to the right people? When, let's say, your security or ops teams look at the graphs, can they tell, is the observability metrics granular enough for them to tell, okay, all of this traffic is coming from Singapore, so okay, maybe some school is having an event, they're all logging in, or all the traffic is coming from Eastern Europe, obviously this is not right. So that's a question of all observability tools, and that's your experiment, right? So you run your experiment, you've got all the evidence, all the data about whether, what has been happening, you've written it all down in the document we talked about. Now the next step, experiment's over, right? Let's say you ran the experiment, your application managed to scale out, it was all good, your hypothesis was verified. And after the experiment is run, very important to learn and verify. So there's lots of different things you can do here, there's lots of different questions you can ask, but here are just 6 of them that we think is quite helpful to think about, right? So what happened? So you can you should write in detail what exactly happened. At this time, we simulated traffic from this region. And this 5 minutes later, ops team was paged. They woke up, they looked at their Splunk dashboard, they looked at their CloudWatch dashboards, they tried to figure out what's going on. At 5 minutes after that, all the instances scaled up. Throughout this whole thing, our latency was X amount. So that's what happened. What was the impact to our customers? You can say, okay, there's no impact because our system scaled up. Very good. What did we learn? Okay, what did we learn? Maybe you learned that maybe our observability wasn't granular enough for us to decide whether it was a DDoS attack or not. Maybe our web application firewall should be geo-blocking certain geographies, because we all our customers are in ASEAN. We don't get any customers from outside that. We should block all of it. And how can you prevent it from happening again? How can you improve your incident response processes? Maybe your ops team, the person who was getting paged responded too slowly because of a certain reason. How do you fix that? And is there anything that can be automated? So, example, there we go. So, returning back to our original example, this is what it could look like after a cryptocurrency mining script was run on an instance. Guard duty detected the activity, generated a finding within 10 minutes, notified the security team, very good. Security team's remediation actions terminating the instance led to increased application latency of more than 0.5 seconds, 0.5 of a second, which is bad, right? So next steps, you want to modify the remediation action to spin up a new instance before isolating the existing one. So this is the improvement point we're gonna make. This is how we improve our incident response processes. What's important at this step, right, and this is a very, very cultural thing, is that this whole learning and verification step needs to be as blameless as possible, right? A lot of times in security teams, we are obsessed with finding the root cause, and we're obsessed with finding who's the person who did the wrong thing and let the whole thing go down. And that's actually really, really bad for security culture and for running chaos experiments. Because I think the important thing to remember when it comes to things like this is that security and availability, observability, these are fundamentally structural things. So if, let's say, something happened because of a misconfiguration, someone accidentally opened port 22, you don't go and find the engineer who deployed who misconfigured the firewall and scold him and give him a hard time. because that just breeds a culture of fear, right? So, kind of a positive culture of psychological safety, what you want to do is, okay, so this guy did this, you can ask him, well, why did you do that? Maybe he was trying to connect the instances for development and he forgot to change it before going to production. Happens all the time. So rather than just blaming him and scolding him, maybe we think of, maybe we should have a guardrail in deployment where if someone tries to deploy something, infrastructure as code, if there's a port 22 open, we prevent that deployment. So that's the kind of mindset you need to have when you're at this learning and verification stage. Alright, now last stage, most important one, is the improving and fixing, right? And this is going to be challenging. I'm not going to sugarcoat it. The important thing is that you prioritize fixing what you've, the findings and what you've learned during the chaos experiment over new features. I know that's very not easy to sell to your leadership, but it's important, which is why right at the start we talked about business metrics, right? So if you can justify the leadership, okay, this problem will lead to this, which will lead to this metric going down, which will lead to X revenue impact, therefore we need to fix this, much easier conversation. Okay, so for our scenario, what they learned after that was that they wrote a run book and they created a piece of automation, and then most importantly, right, is chaos engineering is an iterative process. The most mature organizations are running it all the time. Like for example, in Prime Video in the US, they have live sports events on Prime Video, right? They actually run game days, so simulated events like 5 times a week to make sure that their system can handle it. So, most importantly, you try running the experiment again. You see if your metrics improved, you see if your automation worked, and you slowly improve through that process. So, in summary, where we're here, preparation is really important in incident response, right? I always hear people describe incident response like sports, like a sport, where you have to practice, you have to train, everyone needs to know what they're doing, each incident responder needs to know what tools are available, what teams to reach out to, and today I just wanted to share how chaos engineering is a helpful method for you to improve your incident response processes. So as you run experiments, you collect additional evidence, you continually iteratively improve. As you mature, you can begin running in production, you can begin automating it, so maybe right before every deployment, a certain number of chaos experiments are run. And as you use these chaos engineering approaches to improve your incident response processes, your detection and incident response capabilities should improve as well. So it's vital to be prepared when a security event happens, and chaos engineering can really help you with that. So what can you do next, right? Next, here are some resources. There's a blog post, there's a workshop, and there's a security incident response guide. There's a whole lot of them out there that you can find. And my challenge to you is to go back to your organizations, pick a system, it can be any system, it can be non-production, it can be non-critical, and just try this whole process out of running a chaos experiment on it and see what you learn. So that's all from me. Thank you. This is a nice survey. If you can do it to let me know how I did. If you can't scan it, let me know. I know there's some problems with these things. And yes, I'm right on time, so thank you very much for your attention. I hope you have a great rest of your day and a great weekend, and I'll be here for questions. Thank you.